So we define multiplication of the K numbers in terms of quaternions by adding an element whose square is -1, and then we define the multiplication in the right order, because I forget. AC minus d bar b plus dA plus bc bar epsilon. Okay, so that was a multiplication. Then various properties. So first, some more notation. If x was a Cayley number, then we know the complex conjugate. So let's write x as a plus b epsilon. Complex conjugate of that was a bar minus b epsilon. I conjugate everything except for one. A was a quaternion here. So then we said that, well, furthermore, say the norm of x squared was defined as a norm of a squared plus a norm of b squared. So that's the usual inner product on R8. And then we saw that this is also the same thing as x dot x bar using this conjugation. Okay. What else? It preserved the product, so xy was equal to norm x norm y. So that's what made it into what we call the norm division algebra. Conjugation reverses the order, just like for the quaternions. Okay, that was it maybe. And we also saw it's not associative, for example. But now I want to derive various properties. Maybe first consequence of this rule right here, which is a really important one. It's a strong property. It says that if I take a Cayley number of unit length, then left translation by x and right translation by x are isometries. Because in the usual, kind of obvious notation, right, is I take z and send it to xz. And of course, this rule over there says that Lx z has the same length as length x, length z. Since x is unit length, it's the inner length z, so it preserves the norm, and therefore it's an isometry. So these things lie in SO8, in SO of the Cayley numbers. Well, first, of course, maybe one should say first it lies in O of the Cayley numbers. It preserves the length, right? But it also has determinant 1 because I can connect that to the identity just by letting the unique Cayley numbers go to 1. Right? It's an element SO8. One consequence that, for example, has is that SO8 is diffeomorphic to S7 cross SO7. This is kind of similar to a fact we discussed earlier, that SO4 is diffeomorphic to S3 cross SO3. Diffeomorphic but not isometric. Right, so this here is in the next step of the same phenomena. So how can we do that? So by using these isometries, you have these natural isometries here. So if I take a unit Cayley number at an element in SO7, I can just compose. And so of course, so the element in SO7 I should put into SO8. So let's put it in block form like this, and compose here with Lx. In front or afterwards. So So I claim that will give you a diffeomorphism. Let's see how I go backwards. Let's take an element B in SO8. How do I go into a unit carry number and an element in SO7? Well, let's see where the image of 1 lies, right? This here means I want to put it into SO7, which means I want to make it fix the first Killian number, right? So I can do that by taking by taking B composed with, let's see, before or afterwards, maybe afterwards. Left translation by B of 1 inverse. And left translation by B of 1. So let's look at this element right here. Right. So B went from SO8, from Killian numbers to Killian numbers. It's an element in SO8. And if I look at this composition, then of course it takes 1, 2, 1. Right? So it takes 1, 2, B applied to B1 inverse. Let's see, should I do it the other way around? Yeah, I probably won't do it the other way around. Let's see. Yeah, if we do it this way, it takes this one to B1 inverse B1, which is equal to 1. So let's reverse the order. So anyway, it's an element that fixes 1, so it takes the imaginary Killian numbers to imaginary Killian numbers. So it's an element in SO7, right, fixing 1. So to each 8 by 8 rotation, I can associate naturally a 7 by 7 rotation by fixing 1 vector using left multiplication. And then if I put in the other component, I get a bijection like this. Okay. Of course, again, they aren't isomorphic as Lie groups, right? This is not even a Lie group here. Union Killian numbers aren't associative. So just as a manifold, right? It's nothing to do with the Lie group structure. Okay. Now I want to write down a sequence of consequences of this, these properties of the Killian numbers that we're going to use to derive properties of the automorphism group. So let's see, maybe I'll write them over here. So I guess as step 1, let's remind ourselves that x times x bar is norm x squared. Norm xy is equal to norm x norm y. And xy bar is y bar x bar. Let me just write down all the equations. X in a product of the right multiplication of the W. Comes out like this. Similar for left multiplication. So of course, this follows right away. Let me add one more statement over here to this. So this tells me what the inner product looks like in terms of multiplication. It's x times x bar. But what the norm looks like, but what's the inner product? Actually, that's a real part of x times y bar. But we know that this inner product here is the usual inner product on R8. It comes from the usual norm on R8 comes from the usual inner product. So here on the left-hand side, I mean the usual inner product on R8, and on the right-hand side, I claim that's how I compute in terms of Cayley number multiplication. To see that equality here, you can use a general argument which will come in handy later on also. So if I have two symmetric bilinear forms, let me write down over here. So if B1 and B2 are symmetric plus bilinear, and they agree on the diagonal, this implies that B1 is equal to B2. That's usual symmetrization procedure if I take a bilinear form. So as long as it's symmetric, I just check along the diagonal. Right? So now you observe that both the left and the right are bilinear and symmetric. It's the same thing as real part of yx bar. So both left and right are symmetric bilinear, and along the diagonal they agree, and therefore they agree everywhere. So that's how I can compute the inner product. Because I can also write this as 1/2 xy bar plus yx bar. Right? Because whenever I have a Cayley number, if I add its conjugate, I get the real part of the Cayley number. Just like for complex numbers. Okay. So here I can also see again, well, this is simply true because both left and right are symmetric and bilinear in the x and y. It's just true simply since symmetric and bilinear in x comma y. Switch x and y, get the same thing on left and on the right. Right here it's symmetric bilinear, that's symmetric bilinear. When x is equal to y, then it's just norm x w squared is norm x squared norm w squared. That's on the diagonal, it's just this rule right here. So I imply this rule via binarization.
For the last one, don't you need to use the conjugation symmetry?
Say it again?
For the last part, don't you need to use that conjugation symmetry?
For which part?
For the last one, because when w comes out from the left, the expression goes to the sides.
What are you doing?
In the last one, I see w sheaves x times w1.
Yes? You ask me why this is true or what?
No.
This one here?
Yes.
By the same argument, it's bilinear in x and y. Or do you mean why this and this is the same? I'm not quite sure what you're worried about. I'm not using conjugation at all here.
What?
I'm not using conjugation in this argument.
The first one is straightforward from the computation.
This one.
Yes.
And this one is the same proof. What's the proof? It's bilinear in x and y and symmetric in x and y. Check on the diagonal, and there's just this equation here. Next is that the transpose of right translation by W is right translation by W bar. The transpose of left translation by W is left translation by W bar. So let's write that down as an equation. So if I multiply with W on the right here, that's the same thing if I bring it into the side, but conjugate. So I would say that right multiplication by W, the transpose is W bar. And then similar for left multiplication. Okay, so let's see why this is true. So let me just check this one, of course. Now the trick doesn't apply because it's not symmetric. Right? So it's not quite as, I can't say just look at x equal to y, it's not symmetric. So first I observe it's true if w is real. So I can assume w is imaginary. W bar is minus w would be the same thing. It's linear in w, so break it up into real and imaginary part. So let's assume that's the case. What does that mean? That means it's equivalent, in fact, to saying that the inner product between 1 and w is equal to 0. That's if you want to follow this from this here, right? X equal to 1. So that's equal to 0, which means that I can use part 2 here to say that, so we'll choose x equal to 1. We're switching the names, right? So let's call w, I guess, z. Z, comma, this implies z, comma, zw is equal to 0 for all z. Is that right? So x is 1 and y is w. Right? X is 1, y is w, and w, this is anything. Okay, so that would be equal to the inner product here, but with the inner product is 0. So that means I can argue as follows. This is 0 because this was true for all z. So I put x plus y into there. So this becomes what? Again, I complied this xw is 0 by the same rule. yw is 0 by the same rule, and I only get the off diagonal terms. So x yw plus yxw. What are we trying to prove? We're trying to prove 3 in the case where w is imaginary, and we're almost there, right? Because this here is equal to xyw minus yxw bar. Right, I can replace either w by w bar because I assume w is imaginary. So that's equal to 0, so the two sides are the same. And of course, this is symmetric here. Okay. So that in particular, say, this means in particular, say, so if w is an imaginary Arcadian number, this implies that left translation and right translation are skew-symmetric. So then w bar is minus w, these are skew-symmetric matrices. So that's another useful property of Arcadian numbers, they're skew-symmetric. Property 4. If x and y are orthogonal, this implies that xy bar is minus yx bar. In particular, if x and y are imaginary Arcadian numbers, which are orthogonal, this implies that they anti-commute. So imaginary, orthogonal, imaginary Arcadian numbers anti-commute, just like ij or ik and so on. Right? This is an easy consequence of the definition of the inner product. xy is equal to real part of x y bar, which was 1/2 xy bar plus y x bar. So the inner product is 0. These two are the same. Xy bar is minus y x bar. So that's a simple rule. Now comes a funny rule that turns out to be useful. It's kind of a partial associativity. Remember, I can't put brackets anywhere I want to. They're not associative. But in this case, I can. It's like if I put these together, it's norm y squared, as if I were allowed to do that. Right, so here's one case where I can do it. Similarly, if I do it on the left, to see that, take an inner product with z. So show that it's true by taking inner product with anything. Well, right multiplication is, if I put this on the other side, I pay by the transpose. This is z, y. This is this equation right here. On the other side, pay by the transpose. And this is xy times zy, so now I can use this rule right here to say that's equal to inner product between x and z times norm y squared. That's this rule right here. And now I can bring it inside. So that's, bring this inside here, that's just a real number. This is true for all z, and then applies a claim. So now this thing must be equal to this. So just take the inner products with any element. Now comes the important rule, why when you can now prove why it's called a norm division algebra. Why does it have an inverse? Right, so I claim here's a formula for an inverse. X inverse is equal to x bar divided by norm x squared. And further, I can solve equations. So if xw is equal to z, this implies that w is equal to x inverse z. Just like, so you can solve equations just like you would expect. That now follows from 5, because let's prove that this is the inverse. So I have to prove that x bar divided by norm x squared times x, that must be equal 1. That would be the inverse. So I write this as well, I guess that part is clear. So that's x bar x divided by norm x squared, and that's equal to 1, because that's the norm x squared. But let's see why this is true here. For this I need rule 5, I think. So I want to claim that this is w. So I have to plug in x times what we claim w to be, which is x inverse times z. X inverse is x bar divided by norm x squared multiplied by z. And so this, of course, is a real number. I can take this out. But now I have an expression x times x bar times z. And now I have to use rule 5. That, well, if I have that, that's this rule right here. It comes out as norm x squared. Okay. So that shows that when I plug it in here, I get the solution. So I need some partial associativity even to prove that I can solve equations like this. So that's now justifies a non-division algebra. I can divide things. One more rule. It's a little bit funny. Keep everything on this block here. Maybe I put it. Oh, okay. X y bar w plus y x bar w is equal to 2xyw. You can also do it the other way around. So wy bar x plus w x bar y. So I switch the x and the y around here, and the result is the difference. It differs by an inner product. 7 is also easy, I claim, because notice that, so let's concentrate on this equation right here. It's bilinear and symmetric in x and y, I claim. Right hand side, certainly, right? Notice here, if I switch x and y, this term becomes this term. Switches them around. Therefore, the sum is symmetric and bilinear. So, proves both sides. Are symmetric plus bilinear. So it means I only have to check it when x is equal to y. And when x is equal to y, it becomes one of the other rules. It becomes 5, right? X bar w, y, x bar w becomes this one twice, so I have twice times ln of x squared w. So use 5. Okay. These are all the rules I need. Now I want to derive some consequences from these rules. Maybe this is more than a rule, maybe say a proposition. If A inside the Cayley numbers is a subalgebra, which contains a unit, and epsilon is an element of A perp of length 1, then first the Cayley numbers are the direct sum of A and epsilon times A, orthogonal direct sum. So in other words, A epsilon is orthogonal to A. And the multiplication is then the way it's supposed to be. So if A, B are in A, then A plus B epsilon times C plus D epsilon is given by this rule over there. Right. So in other words, it says that there's only one way I can possibly define this multiplication here. It's forced upon you, the rules for multiplying.
You mean a quaternion subalgebra?
Pardon? No, any subalgebra.
Real?
Any real subalgebra, right. Well, it's okay, let's say, okay. A is a subalgebra 1 in A, then A times epsilon is orthogonal to A, and this holds. Let's write it out, maybe just. So I'm not saying that they span. What am I saying? I'm not specifying the dimension of A. Just take any subalgebra. It could be the reals, the complex numbers, the quaternions, or any such other subalgebra inside there. It has to have at most half the dimension, right? Because I can take something orthogonal to it. When I do, epsilon times z is orthogonal to it. If A is 4-dimensional, that gives me the whole clear numbers. If it's less, it's smaller than that. But then multiplication is forced upon you, like this. So let's maybe just indicate what kind of things do I have to prove. Maybe I'll do one or two. For example, I have to show that B epsilon times D epsilon is equal to minus D bar B. Right. This times this is supposed to go right here. That'll be one of the rules. How does that follow? That has to be the case. Okay, let's see. First I claim, so let's start the left-hand side, B epsilon times D epsilon. I claim it's equal to epsilon B bar times D epsilon. So why is that? Well, B and epsilon were orthogonal. And of course, this was 1/2 B epsilon bar plus B bar epsilon. Right? But epsilon bar is orthogonal to 1. Right? 1 is contained in A. Epsilon is orthogonal to A, so epsilon is also orthogonal to 1. So that means that B epsilon. Okay, so this is at right, minus B epsilon plus B bar epsilon equal to 0, which means B epsilon is equal to epsilon B bar. I guess I want the other way around. Do it the other way around, right? Could do it epsilon B here. Let's see. And now I have an epsilon B bar here, and this is minus B epsilon. Okay. That implies this equation right here, that these are equal. So next, I claim this is minus epsilon times D epsilon bar times B. So in other words, I'm switching this around with this here. And that uses, which rule is that? This rule right here. Right, so let's see. When can I switch them around? When they're orthogonal. So notice here, I'm using here the fact that B and D epsilon have inner pod at 0. Right. This here lies in A, and this lies in epsilon times A. So they're orthogonal. So then since they're orthogonal, that means I can, this right-hand side is 0, and then I can switch around these two here and pay the minus sign. Okay. What next? We want this to be okay, now I can say, well, I'll conjugate this out. Minus epsilon times epsilon bar D bar times B And now I can use the rule, which was it? This rule right here. Right? Epsilon bar times epsilon, that comes as norm epsilon squared. Epsilon has length 1. So that is minus d bar b. That's what I wanted. Right, so I have to combine all the rules in order to see that the multiplication rule is forced upon me. Just from the fact that it's norm-preserving, that's all I'm using here. Everything's based on the fact that you have a normed division algebra, it preserves a norm. If you look at consequence of that, this rule here that I started out with is forced upon you actually, just from these rules and from nothing else. There's several others I have to verify, but it's a kind of the same kind of procedure. Well, I guess maybe I should have started with the fact that A epsilons are orthogonal to A. Right, so what does it say? It says that A B epsilon is equal to 0. But that's because I know that 1 epsilon is 0. So epsilon is orthogonal to A and orthogonal to 1, so 1 epsilon is 0. This means that, what rule?
B minus 1 times A less than A is orthogonal to epsilon.
Yes. Okay. Yeah, so let's write this as B bar A, I guess, times epsilon. From putting on the other side, I have to conjugate. This is an element in A. This is an algebra. And because, so conjugation, here I'm also using that if, say, B is an element in algebra, this implies that B bar is also an element in algebra, since 1 lies in the algebra. That means conjugation preserves the algebra. So this lies in the algebra, and epsilon is chosen to be orthogonal to the algebra. So therefore, these are orthogonal. So that is this and this are orthogonal. Okay. Particularly, it says that if I let A be the quaternions, it doesn't matter what epsilon it shows orthogonal to the quaternions, I always get the same multiplication rule. It's forced upon you. That's what this says. So now let's use that to describe the automorphism algebra. That was my goal after all. So we define G2 to be those linear maps which respect multiplication automorphisms. All the Kelly numbers. Okay. So, is there a question or comment? First, G2 consists of isometries. In fact, lies in the isometries of the imaginary Kelly numbers. And B, the important part is that given E1 and E2 Cayley numbers such that they are unit vectors, they are orthogonal, let's say, let's put a third one in here. So we have 3 Kelly numbers. And such that let me say it like this maybe. 3 K numbers which are orthonormal. So they're all 3 unit vectors, they're all orthogonal to each other, so orthonormal in that sense, and such that E3 is also orthogonal to the product E1 times E2. Then, so given 3 such things, then there exists a unique automorphism such that A of I is E1, A of j is E2, and A of epsilon is E3. I want to uniquely characterize what an automorphism does. I have to say 1 goes to 1, it's an automorphism. Right? I have to say where does I go. If I show it's an ensemble, it's going to go to unit vector. Where does j go? It's going to go to another unit vector. Since I and j are orthogonal, E1, E2 must be orthogonal. Right? But of course, E3, I times j is k. Right? That means that E1 times E2 is going to be where k gets sent. So this must be orthogonal to it also. So let me. Let's first prove sinusometry because I need that in the next argument anyway. So certainly it takes 1 to 1, it's an automorphism. I want to claim that it takes imaginary numbers to imaginary numbers, which of course will have to be part of the claim. Well, how can I characterize imaginary Killian numbers? Notice that x times x bar, which was norm x squared, is minus x squared if x is imaginary. Right? So, or in other words, x squared is equal to minus norm x squared. Particularly, it's real. So, a square of an imaginary number is a real number. And I claim that characterizes imaginary Killian numbers. Maybe first let's convince ourselves AX has the same property. So let's see if AX satisfies an equation of this type. Let's take AX multiplied by AX. That's equal to A of x squared since it's an automorphism. X squared is minus length x squared, but that's real. A takes 1 to 1, so it's minus length x squared. Okay. So it at least says that AX is a Killian number such that its square is something real and negative. And actually this implies that AX is imaginary. So let's see, let's have a side discussion why that's the case. Let's write a Killian number as A plus Y, where A is real and Y is imaginary. So when I square it, that's A squared plus Y squared plus A is real, so I don't have to worry about it commuting or anything, it commutes, plus 2AY. If that's real, how can this be real? Well, that's certainly real. Y squared, well, Y was an imaginary Killian number, that's real. So this part here lies in R. So that would mean that 2AY would have to be in R. But how can that be? That Y is imaginary. I have a multiple of imaginary number. It can be real only if either A vanishes or Y vanishes. But if A vanishes, that's what we want. If Y vanishes, then X is A already. So this implies that A or Y is 0. that of course, if y is 0, the square is positive, right? If a is 0, the square is negative. And here we saw that the square is negative. So this implies that ax is an imaginary Carry number. So it preserves imaginary Carry numbers. And now I only have to verify that it's an isometry on the imaginary Carry numbers. For this, I use the following equation: x squared plus norm x squared is equal to two x1 times x. And this is rule, one error erased, rule 7 probably. Yes, this is one of the specialties of rule 7. As long as x is imaginary. Of course, now the right-hand side is 0, right? X is imaginary, so it's orthogonal to 1. So x squared plus norm x squared is 0. Well, we already knew that. Oh, in fact, I'm repeating myself, right? We've already done. Look at this. This is equal to, so what's norm ax? I already know it's imaginary, so it's minus ax times ax. This was a general for an imaginary number. The product by itself is minus the norm. Now I can say again that's minus a of x squared. It's minus a of minus norm x squared. So it's a of norm x squared. That's a real number, so that's x squared. So norm ax is the same as norm x. It's an isometry. So just because it's with respect to multiplication, it must be an isometry. Kind of surprising. Okay, so now we have an isometry, and now let's let's see why B holds and why it's so useful. So let's just first justify the rule. E1 goes somewhere to another unit vector, it's an isometry. J goes somewhere to another unit vector, it's an isometry. These are orthogonal, these must be orthogonal. K must go to, it's an automorphism, to the product E1 times E2. Ij and K are orthogonal, so these three must also be orthogonal. That's why I'm adding the rule that E3 must be orthogonal to E1 times E2. And then epsilon goes somewhere that we call E3, right? And I, j, k, and epsilon are all orthogonal to each other. These four better be orthogonal to each other. So E3 must not be only orthogonal to E1 and 2, but also to the product. Okay, so that's what this is. And the theorem says that that's sufficient. That's an if and only if the automorphism is uniquely characterizes, where it sends I, j, and epsilon, as long as I add the fact that E3 must be orthogonal to E1 times E2. So I claim this follows from the proposition I just erased. Remember what it said? Let me just write it down. So it said I had a subalgebra inside the Cayley number, contained 1, an epsilon orthogonal to A. And then multiplication was prescribed. As you would expect it from the Cayley numbers. That's what it said.
You want A to be a homomorphism, right?
Pardon?
You want A to be a homomorphism.
Yes.
So you have also defined I times epsilon, J times epsilon, K times epsilon, and epsilon squared. So you have defined A.
You define the linear map. Correct. Now I have to show it's an automorphism that respects multiplication.
You have defined this in order to respect.
Now there are many other products. Why does it preserve all the products? You define it on a basis now. That's correct, but why?
K, I, epsilon, J, epsilon, K, epsilon, and epsilon squared.
That means you have the linear map now. Why it's an automorphism?
You must only check it in products of elementary elements. You don't have to check on sums.
Yes.
Linearity.
Yes.
And on the generators, it is defined as a morphism. It is compatible with the product. At least in the given order, maybe we should check the other way around.
There's some kind of ambiguity, isn't there? I could write something as an inner product in several different ways, and I have to show it's consistent. That I can write, if I take a product, why does it preserve product structure if I just define it on that basis like that?
I mean, if you change the base, that's the problem.
Well, then I'd have to argue things like, well, okay, I have I, j, k, epsilon, I, epsilon, j, epsilon, and k, epsilon. And it goes into the corresponding thing that's required to be an automorphism. If I multiply this times this, what does it go into the product?
Why?
Why does it go into the product so this now goes into the prescribed element, right? Now multiply these on the left-hand side here. Why is the image the product of the images?
You define
No. That's an additional multiplication.
you define it to be E1 times E2. Why?
That's correct, but now I have to check the whole thing is an automorphism. Particularly it says if I multiply this times this here, I know where this one goes, I know where this one goes. Why does a product go to the product? That's a priori not so clear. Okay, so that's the issue.
Use the theorem for the opposite algebra generated by I, J, K, and 1.
That's what I'm trying to say here. This proposition tells me that if I know a subalgebra on which multiplication is respected, if I take any, no matter what element I take orthogonal to that, the multiplication looks the same. Right, so in other words, here I would say, well, take takes A to be H, take A prime to be 1, E1, E2, and E1 times E2. Then take epsilon to be my element, or A per, my standard element if you want to. And I take my epsilon prime, orthogonal to A prime, to be what do we call it, E3, which is now orthogonal to A prime by definition. Okay. And now the rule for A and epsilon is like this. The rule for A prime and epsilon prime is the same way. So therefore it respects multiplication. Okay. What do I call it? Okay, so let's now derive some consequence of that. So I know kind of geometrically what automorphisms do precisely, right? They take special three frames to special three frames. Those where the third vector is orthogonal to the product of the first two. That tells you something about the topology, for example. Well, various consequences, maybe. G2 is compact, simply connected, and the center of G2 is trivial. So let's see how we can prove this. I claim compact and connected are clear, right? I can take E1, E2, 3 arbitrary as long as E3 is orthogonal to the product of E1 and E2. So of course I can move such a 3-frame continuously to the 3-frame I, J, and epsilon. Right, so every automorphism can be continuously moved to the automorphism which is identity. So I can find this the family takes this to I, J, and epsilon. It's compact, again, because it's described by 3 orthonormal vectors. Right? So if I take a sequence of such linear maps, the image is just given by such 3 orthogonal vectors again, and therefore corresponds to an automorphism. So compactness is clear. Connection is clear. Simply connected. Let's take a look at the structure that this implies. So I claim, let's take an element G in G2. That means I have an E1, an E2, and an E3. And I send this into the first 2 vectors. Okay. Those are 2 orthonormal vectors, so that's what's called the Stiefel variety of 2 frames in R8. In the Kelly numbers. Instead of 2 frames. 2 orthogonal unit vectors. This map is onto, right? No matter if I give you E1, E2, I can certainly have an E3 that's orthogonal to E1 times E2, so it's onto. And what's the phi of this map? So what freedom do I have? Pick E1, E2.
S4.
S4. It's a sphere of a certain dimension. Let's see. I give him 2 vectors. That's a 2-plane in R8.
And how the third one as a product?
Third one as a product must be orthogonal to that. So I have a 3, R5. So it's a 4 sphere. Yes. Okay. So, right? So I understand what he's saying. E1, E2, I know that E3 must be orthogonal to this, and its product. That's a 3 space in R8. So it must be orthogonal to that, which is an R5, a unit vector. So it lies in S4. Furthermore, for example, for the Stiefel manifold, I have another vibration which takes this into its first vector, which is S7. It's a unit vector in RH, in the Cayley numbers. What's the fiber? Well, it's a vector orthogonal to that, unit vector orthogonal to that, so that's S6. Okay.
So it's infinite.
So I have two fibrations, this one right here, and this one right here. So now I can use a long homotopy sequence for homotopy groups. In fact, let's see how many are 0 for the Stiefel manifold. This is 0 for I is equal to 1, pi 5 is 0, up to 5. So for these Stiefel manifolds, the first 5 homotopy groups are 0. Now I can go to this vibration. Something's wrong. The dimension of G2 is supposed to be 14. And right now, looks like it's too much. Some dimensions are wrong. I have dimension 17 right now, right? Dimension of Stiefel manifold will be this plus this is 13, plus 4 is 17.
The problem is the extra orthogonality condition imposed.
Ah. This is not quite exactly what I wanted. Can E1, E2, and E3 really be any Cayley number? Imaginary. I know where 1 goes to 1. So this better not be one of not be 1, right? These must be imaginary Cayley numbers. I, J, and K, that's what you're thinking of, right? So they must be imaginary. So here I take the imaginary Cayley numbers. So now the fiber is 1 less, it's S3. And here again I take imaginary Cayley numbers. So this is now unit sphere in imaginary one, that's 6, and the fiber is S5. 6 plus 5 is 11, plus 3 is 14. There we go. So now it's 14 dimensional. And now the first 4 homotopy groups of the Stiefel manifold are 0. And this implies that pi 1 of G2 and pi 2 of G2 are 0. Pi 3 is not so clear anymore. Well, in fact, you can see what pi 3 is. Right, what if I look at the level of pi 3, goes to 0, comes from pi 4 of the Stiefel manifold, which is 0. So it's equal to z. So pi 1 and pi 2 is 0, and pi 3 is equal to z. We can add this here. In fact, this last fact here, if one knows a little bit more, implies that G2 is simple. Which otherwise is not immediately to see. There was a fact that's in one of the order exercise. If G is compact, non-abelian, this implies that H3 of G is non-zero. Notice here pi 1 is 0, pi 2 is 0, pi 3 is 0. That's the same thing as H3 of G by the Hurwitz isomorphism theorem. But for every simple Lie group, H3 is non-zero. If it wasn't simple, it would be the product of two simple things, at least up to covers. But then H3 would be Z plus Z, or would certainly be bigger than Z. Let's be a bit careful, because what does it mean to not be simple on the level of Lie groups? On the level of Lie apples, it means the direct sum of two simple ideals. On the level of Lie groups, it's true up to covers. So it's not quite a proof, but it at least illustrates why it should follow. The center of G2 trivial it was also supposed to be a consequence of this kind of characterization of G2, but I couldn't see it anymore. In my notes, I have something scribbled there that it's clear, but I didn't see anymore why it's clear. So taken automorphism is described by E1, E2, and E3, and assume it commutes with every other such automorphism. Then you have to choose the other one somehow in a clever way to see that A must be the identity. That's what I was able to see at one point, but not anymore. You can think about this as an exercise maybe. This is supposed to be easy, if you do it just right. Okay. Maybe the last thing I want to mention about exceptional Lie group is a definition of F4. Not going to prove anything about it, but at least I want to have you see one definition of another exceptional Lie group. So let's look at the following vector space. Matrices with elements in the extonians, which are skew emission. So 3x3 skew emission Cayley matrices. Okay. So that's a vector space of real dimension 27. Right, 3 Cayley numbers plus 3 real numbers. Now the problem is that this is not invariant under multiplication. So if you have two matrices in H, then in general A times B is not in H. But if I take the symmetric product AB plus BA, this is an element in H. And that's often denoted as A circle B, a symmetric product, symmetrized product of two matrices. And now I can define F4 as the automorphism group of this vector, this product structure. So GLH with the property that G of A sub B is equal to G of A. insert G of B. So F4 is again in a certain interpretation automorphism group of a certain algebra. But this is a little more difficult to work with. To prove corresponding things for F4 like this here. It takes a little bit more work. There's one paper in my references by Murakami. If you want to read more about this. He has everything you want to know about G2 and F4. A whole paper, like 50 pages about G2 and F4. It's well written, but maybe more detail than you want to see. But if you want to look up something, everything about G2 and F4 is in there. Okay, I don't want to do any more exceptional loops. I want to go back to the next subject, which is semi-simple Lie algebras. And for this I have to do a few things about nilpotent and solvable Lie algebras, which I'll do fairly quickly, so that we can get to the main part, which is the semi-simple Lie algebras. So maybe I'll start thoroughly on Wednesday then with the semi-simple ones, with the nilpotent solvable ones.